Hello everyone, I hope you're each doing well. In this slideshow, I'm going to be reviewing correlational research and experimental research. So let's start with correlational research. So we can make a prediction that if ice cream sales go up, that drownings are likely to increase as well. So you can see here, we could take this data and we can plot it onto a graph with our x-axis and our y-axis. And it looks like as one thing happens, another thing is happening. So you can see that as drowning deaths go up, so too does consumption of ice cream. And also as drowning deaths go down, so too does consumption of ice cream. So this is called correlational research. And the question is, does this mean that ice cream sales are causing drownings or that drownings are causing ice cream sales? Or is there some third variable that explains this relationship? So think to yourself, what is that third variable that might be causing this relationship? So I'd like for you to click on correlation in the news. And when you do this, you'll find that there's a brief video clip that can help you to further understand this concept and how it might affect human behavior. So correlational research results in what's called a correlation coefficient. So a correlation measures the relationship between two variables and does not mean causation. A correlation coefficient can range between -1 and +1, and the closer the number is to 1, whether it's positive or negative, the stronger the relationship. And a correlation coefficient of 0 or close to 0 means that there's no relationship. So as we move closer to 1, whether it's positive or negative, that tells us that there is a stronger relationship. So a correlation coefficient of, let's say, positive 0.9 is stronger than one of negative 0.2. On the other side, a correlation coefficient of negative 0.9 is stronger than a correlation of positive 0.2. So you see here that it's not the sign that's important, but the number that's important. So here's an example of correlational research. So we have two variables and we collect data on these two variables. So let's say that we collect data points on education and income. And so we might expect that the more education a person has, the higher their income level. But the question is really, with just correlational research, is it that education causes higher income? Or is it that higher income leads to more education? Is it that when people already have higher income, they're more likely to get more education? So we don't really know which is causing which. Here's another example, smoking and health. So we would assume that the healthier a person is, the less likely they are to smoke, or that the less likely someone is to smoke, the healthier the person is. Again, we don't know which is causing which, and that's one of the problems with correlation. First of all, we know correlation does not mean causation, and then we also don't know if there is causation, which is causing which, or if there is that other variable that might be causing the relationship. So perhaps there's something else about smoking and health that's causing those two to be connected. So there's two components to a correlation coefficient. The first is the sign. And so a positive correlation means that two variables vary in the same direction. So that means as both go up, as one goes up, the other one also goes up, or as one goes down, the other one also goes down. A negative correlation means that as one variable goes up, the other variable goes down. So I'll be looking at some examples of that here in just a moment. And then we have the number. And again, like I said a moment ago, the number tells us the strength. The higher the number, regardless of the sign, the stronger the correlation. So for example, in a correlation of positive 0.5, this means that with exercise and health, that the more a person exercises, the better their health is. But again, we don't know, is health causing more exercise? Do healthier people, are they more likely to exercise? And this is a moderate relationship because it's somewhere between 0 and 1. And they're both moving in the same direction. Another example is negative 0.9. And these are made up, by the way. I just use these as examples. And so we see here that one variable, which is stress, and another variable, which is memory, are moving in opposite directions. So the more stress a person has, the less likely they are to remember. And so this is, I think, an example that it may not be as strong as negative 0.9 if we actually did a research study, but you can see here that what's happening is that one is going up, the other is going down, and if it is negative 0.9, that means it's a very strong relationship. So let's look at some examples. Which correlation coefficient is stronger, positive 0.1 or negative 0.5? So the answer to this is that it is negative 0.5 because it's closer to 1. Remember, we're not looking at the sign. Another example, positive 0.9 or negative 0.8. In this example, it's going to be positive 0.9. We're not looking at the sign. Again, we're looking at what's closer to 1. The next one is positive 0.4 or negative 0.2. So if the answer is going to be positive 0.4 because it's closer to 1. And then we have positive 0.3 or negative 0.1. And which one is stronger? It's going to be positive 0.3. And that's because it's closer to 1. So let's take a look at negative and positive correlation. So let's go through some examples. The more ice cream you eat, the more likely you are to drown. So ask yourself, is this a negative or a positive correlation? So in this example, this is a positive correlation. And you can see I have this particular one highlighted in blue. We have one thing going up and the other is going up as well. And we can go back to that slide that I had in your mind. You can go back to the one where we had the graph where the data points were plotted, and you would see that as one is going up, ice cream, sales or consumption, the other one was going up as well. And as one was going down, the other was going down. So when something is positive, that means that they're both moving in the same direction. The more students study, the higher their test scores. Is this positive or negative? So this is a positive correlation. Why? Because one thing is going up and so too is another. Here's another. The more time children spend outside, the better their mood. So what we see here is that one thing is going up and the other is going up as well. We might also see that the less time children spend outside, the worse their mood. And here's another. The more that people smoke, the greater the risk of developing lung cancer. So this is an example of what? Positive or negative? It's an example of positive correlation. And the reason it is because as one is going up, the other one is going up as well. How about this one? The more vitamin C a person takes, the less likely they are to have a cold. So what's happening here is we have one variable going up and the other one going down. That means the correlation is it positive or negative? It's negative. And that's because negative correlations happen when, or are called negative when one variable goes up and the other one goes down. And then we have the more time you spend inside with groups of people and without a mask, the more likely you are to get COVID. So these two variables are moving in the same direction. So is this positive or negative? It's positive, and it's positive again because they're both moving in the same direction. Now, these are just examples that I made up. This is not to say that any of these are true or not true. I just use these for purposes of application. So some things to remember. Correlation cannot prove causation. So if all we do is collect two data points, we don't know, for example, if video games and academic achievement, let's imagine we collect those two data points, we don't know through correlation if one is causing the other. For example, increases in video game playing may be related to increases in or decreases in academic achievement, or it may be that children or adolescents who already have low academic achievement tend to spend more time playing video games. And again, this is just an example. I have not read research that suggests this. This was just to demonstrate negative correlations and the problem with determining causation. Here's another. Does playing video games cause more aggressive behavior? We hear this often. We hear about violence on TV causing aggression, violent video games causing aggression. But if all we're doing is collecting two data points from that type of research, we can't determine if one thing is causing another. All we can do is say that they're related, and there may be another explanation for that relationship. Maybe children who already are more aggressive are more likely to want to play certain types of video games. So we don't know, or there may be some other variable that explains the relationship. The only way we could determine cause and effect is if we were to randomly assign participants into groups. And through random assignment, we might have some children who are playing violent video games, some children who are playing non-violent video games, some children who are playing no video games. And then after a period of time where we hold everything constant, we then measure the variable of aggressive behavior. So that would be more likely to allow us to establish cause and effect than this type of study would, because remember, correlation does not tell us about causation. And there may be, again, this third variable. So those are some of the limitations. But sometimes we do correlational research because it may not be ethical to do experimental research. For example, in the case of smoking, we couldn't randomly assign participants to smoke. We couldn't say, for the next year, we want you to smoke 2 packs of cigarettes a day if you're in our experimental group, and the other group is not going to, and we want to see what happens. That wouldn't be ethical. It's not ethical because we already know that there are toxins in cigarettes that can be detrimental to one's health. So to do something like that, again, would not be ethical. So we have to look at already existing data points, and then that allows us to establish correlation. In the case of smoking and cancer, while we can't do that with humans, you can do those types of studies with animals where they're exposed to certain toxins that are in cigarettes. And we know that animal models show that some of those toxins that are in cigarettes increase one's risk for cancer. So I have a couple of kind of examples here. Someday I want to get married because studies show that married people are happier. A smarter interpretation is that no one wants to marry an unhappy person. So again, you see here, this is the problem of directionality with correlational research. We don't know which direction this relationship is going in. So everybody who went to the moon has eaten chicken. Good grief, chicken makes you go to the moon. So sometimes correlation, there may be things that seem correlated or connected, but they really are not connected at all. It's just sort of by chance. And we could think of these as illusory correlations. So this is an illusory correlation is where people believe a relationship exists when no such relationship exists. So for example, if we look at this chart, we see here that as autism rates go up, so too does our organic food sales. And so someone could take this data, they could make a news article of it, and they could say that they see that there's a relationship. And if someone were to read this article and see this, they may conclude that in their mind that those two things are connected. But there are other reasons that these two things are happening at the same time, as I'm sure you know. But you could think of some examples of illusory correlations in the news where it may be interesting to point out that two things seem connected, and it might actually cause people to think that one thing is causing another. I think an example of this could be autism and vaccinations. And we know that autism is not caused by vaccinations, but yet many years ago there was a study that was done by a man named Andrew Wakefield, and he found that at certain times that children would get vaccinations when they got them, that they were also being diagnosed with autism. And I can't remember the number of participants in his study, but there were just a few. I think it may have been 7. I can't remember exactly. But, and there was also conflict of interest with these participants. And so he suggested that those two things were connected. And we know that this has affected how people today view vaccinations. That's the roots of those concerns come from that study. And some other, and then of course some people who are anti-vaccination advocates. So what's happening though is that around the time that children get vaccinations, that's the time that autism symptoms tend to show up. And so it's not connected to vaccinations, it just happens to be developmentally when those symptoms tend to occur. So just like in this diagram here with autism and organic food sales, it looks like they're connected, but there's not evidence that that they are. A real study that would help us to see this relationship would be one where we might do an animal model, where we might have some animals who are getting whatever's in the vaccination. We know there are lots of products that are in the vaccination, and then other animals that are not, or we might divide up some of the parts of the vaccination and see individually what those components are doing. And then we might measure their certain behaviors in the animals. And that would allow us to see better what the effects are. And again, there's not evidence at this point that suggests that vaccinations are causing autism. We know how important vaccinations are. So if we can ethically do a study, and then also it can be very costly to do a study like the ones I'm mentioning that involve experimental research, then that's the ideal if we want to establish cause and effect. So you can see here, for example, what we could do is, let's imagine that we want to test a type of treatment, a type of psychotherapy, and we also want to know if drug therapy alone works, or is it drug therapy and psychotherapy. We would randomly assign participants into 3 groups. Random assignment is very important in experimental research because it really reduces the chance of bias. If I'm assigning people to a group randomly, then I know that there's not something already inherently present within that group, like group 1 in this example, that may cause them to respond differently to drug therapy and psychotherapy than, say, someone who is not randomly assigned. So random assignment is very important when we're thinking about experimental research. That helps to remove that bias. Otherwise, again, there might be something already inherently existing within that group that makes them behave a certain way that has nothing to do with that variable of drug therapy and psychotherapy. I apologize for that interruption. I clicked the slide too soon. So what you'll see here is we want to control for confounding or extraneous variables. These are variables other than the independent variable that can affect the results of the study. So in our case of studying violence on TV and how it affects aggressive behavior, or whether it does, we would want to make sure that if we have our groups randomly assigned into our experimental and control groups, we would want to make sure that both groups are treated exactly the same, except for that independent variable of violence on television. So if we did a study in a laboratory, we would want to make sure that the laboratories looked identical for both groups. We want to make sure that the seating is identical for both groups, for example, that they're both going to watch television. One is going to watch 30 minutes with violence, the other one is going to watch 30 minutes with no violence, maybe similar themes in the program, so everything is held the same. We'd want to make sure that any experimenter who comes in the room, that they look the same. We'd want to make sure that we tell parents what children should eat or avoid eating before the study. And and the list goes on and on. So we, again, want everything to be as controlled as possible. Then we know, to the best of our ability, that our independent variable is affecting our dependent variable. Now, no study is going to be absolutely perfect, where you can control every single possible thing, but you want to be sure to control as best you can. Otherwise, you really can't say that the independent variable is causing changes in the dependent variable. And then we also want to make sure that our study follows ethical guidelines. Make sure you read about that in your textbook. These ethical guidelines include things like preventing people from experiencing psychological or physical harm, also including informed consent, where people know about the risks of the study, where they also know that they can withdraw without penalty at any time. There is particular protection for vulnerable groups of people, like children, people who have developmental disabilities, prisoners. So those are that. I would like for you to be sure to read about that in your textbook. So let's look at some examples of independent and dependent variables. I think when you take your test, I may ask you, I think it's going to be important for you to know what these mean, what these are, and I'm going to ask you to be able to apply these concepts. So I might give you a sample of a study, and then you need to identify the independent and dependent variables. So here we have melatonin and reported sleep quality. So we have melatonin, that's what you as the researcher have direct control over. There in the experimental group is going to be getting perhaps 2.5 milligrams of melatonin. The control group may get 0, or and they would be getting a placebo, And we use placebos because we know that there's something called the placebo effect, where just the act of taking that pill, or or it could be a substance that could affect behavior. So we want to control for that. Again, holding everything constant. We may have more than one experimental group. Maybe one group gets 2.5 milligrams of melatonin, one group gets 5, and then the other gets none. And then our dependent variable is going to be reported sleep quality. So we're going to measure this in a very systematic way. We're not going to just casually ask, so how did you sleep? We may have a survey where we can quantify this, where we can measure with numbers, knowing exactly what their sleep quality is. And we would want to choose a measurement that's probably already been used before, because if we came up with our own, there may be problems with reliability. Is this a good measure? When people develop scales, by the way, it does take, that could be a study in itself. So if you are in the future going to be doing any research, like when you transfer to a four-year university, some of you, when you go to four-year school, may decide to do research in your senior year, a study may involve using a scale, and often it will be an already existing scale, and there are many of those out there. Or a study may involve developing a scale. So here's another one, 30 minutes of exposure to violence on TV. That's our independent variable because we have direct control over it. One group, our experimental group, gets 30 minutes, the other group gets none, and then aggressive behaviors are dependent variable. And again, we want to be systematic in our measurement of aggressive behavior. We want to make sure that when we write our study that we're very clear in how we measured those variables, what those variables are, so that anyone who reads it knows exactly what we mean by aggressive behavior. Because we each have different ways of viewing things like what is aggression or what is violence on TV. And then we have room lighting that we can control. How does it affect mood? We might have different types of room lighting and then measure mood. We have outdoor play. We might say 30 minutes of outdoor play per day versus none, or 30 minutes in the afternoon, 30 minutes in the morning, and then none. So we have 3 groups. And then we may measure self-regulation. We can measure this in a variety of ways. That's an interesting variable to study, and we would probably do this with children. And then we have a memory supplement, and this is, again, the independent variable, what you as the researcher have direct control over. And then the participants in the experimental group would get some level, some amount of the memory supplement, and then we would have a control group with none to serve as our baseline, who would get the placebo, and then memory is our dependent variable. So let's think about some examples here. Here we have depression and an antidepressant. So think to yourself, which of these is the independent variable? That's the variable that the researcher has direct control over. So in this case, the independent variable is the antidepressant. One group, the experimental group, will get the antidepressant at some level. The other group will get the placebo. And so everyone is going to be treated the same. No one will know which group they're in. And we'll talk about what type of study that's called here in a moment. Mood and room color. Which one of these is our independent variable? What do you as the researcher have direct control over? You have control over room color. And so room color is our independent variable, and then mood is our dependent variable. It shows the potential effects of the independent variable. And then finally, we have low-carb diet and alertness. You as the researcher have direct control over the low-carb diet. Maybe one group, the experimental group, gets the low-carb diet. Another group gets no particular diet, and then we compare levels of alertness. And so alertness is our dependent variable. So some things we want to think about with experiments, we want to think about the placebo effect. And this is why we need to have a placebo. We want to make sure that just the idea of taking a particular pill, we want to make sure that we're taking that into consideration. And so we have some participants the participants in the control group who will get the placebo. And then we have the participants in the experimental group or groups who will get some level of the drug. A single blind study. A single blind study is one in which the participants don't know which group they're in, whether they're in the experimental group or the control group, but the experimenter still knows. And then finally, we have double blinding or a double blind study. And this is a double blind study is really the gold standard of studies, in particular of drug studies, so that the experimenter does not know which group the participants are in. They don't know if they're in the control or experimental group when they're administering the placebo or the actual medication. They have no idea, and the participants don't know either. And the reason that this is so beneficial is there can be subtle cues that experimenters give off. And if you're a participant, you're going to try and figure out, based on how that experimenter interacts with you, whether you're in the control group or the experimental group. And you may be able to pick up on things if your experimenter, if he or she knows which group you're in. But if the experimenter doesn't, then they're not going to be giving off anything that may affect your thinking about which group you're in. In addition, there may be things that the experimenter may say unintentionally that could affect the study if they know which group you're in. So double blinding is very important. So if you have any questions about this, please feel free to send me an email. We can talk over the phone. We can have a Zoom meeting individually, but let me know what I can do to help you. I will have a Zoom meeting scheduled for you on Monday, and I'll be sending an email about that. And I look forward to seeing you all. Have a nice afternoon. Bye-bye.